Okay. All right. Today, we're going to do some calculations and discussion about, where's Zoom? There's Zoom. Discussion about energy and momentum considerations in electromagnetic waves. So, how much energy would it take to emit a wave? How much energy would you get if you absorbed sunlight of a certain description or laser beams? How much energy would it take to emit that, to absorb it, to reflect it? And related to energy, we're going to find ourselves also talking about momentum. Energy and momentum. They're very closely related concepts in physics. They're both conserved quantities. And we're going to be talking, maybe we focus more on energy, but we'll always kind of like take a little peek in and say, okay, so what about momentum? Or what is the corresponding set of questions that we might ask ourselves about momentum, although we tend to be more concerned with energy. And just wanted to do a couple things. Let's see here. Let's try to have that up. Okay, and Wednesday is advising day, I should say that. So there's homework this week from chapter 34, 4 questions, and then we're gonna start to talk about some of the waves and ray optics topics, which will be like Thursday's lab. There's also questions about that in this week's homework. That shouldn't be too bad. That's jumping kind of into a very different part of the textbook. That's jumping to chapters 20 or 23. Lots of questions about like frequency, wavelength, and maybe light as it starts to go from one material to another or reflect. And pretty easy questions for the couple, 3 from chapter 20 and 1 from chapter 23. Shouldn't be too bad. So I wanted to bring up, where is this week on a Moodle? This guy right here. And let's go through this, and we'll get to the energy and momentum questions at the bottom of this. I think I'll switch over to that. Have that ready to go, but I'm gonna share the screen and go for this one here. Okay, properties of electromagnetic waves, and there were all sorts of questions, A through H, kind of in 3 chunks. A laser beam with a diameter of a certain diameter at 8 millimeters, a little less than a centimeter, is turned on for 2 seconds and then turned off. So imagine kind of we have a laser beam and the cross section is circular, and it is only a certain length because it's only been turned on for a certain short interval of time instead of just it's been on kind of continually. The magnetic field of the laser's light wave is given below, where all quantities are expressed in standard metric system units. So magnetic field would be Teslas. X is probably referring to the X coordinate, it's a position in meters, and time, T is time, so seconds. And we'll go through these, and like, I think basically you should already be kind of okay, or feel somewhat okay with A, B, C, D, E. And then we'll also get into these questions here. What is the intensity of the wave? What is the total energy carried in the pulse? And what is the total momentum carried in the pulse? And the equations or the concepts from that would come from, I think, like the second half of section 34.6, which is called Properties of Electromagnetic Waves. Okay, so let's go through the first couple here. Let's go through the directional stuff, which is part A and part D. This isn't too bad. This wave, what direction is it moving? The answer to part A has nothing to really do with electromagnetic waves. It has to do with kind of understanding how to read an equation like this, which is some sinusoidal function of x and t, or sinusoidal function involving position, coordinates, and time. It doesn't even really matter that it's sinusoidal, by the way. This is going to be some sine wave. This is going to be the amplitude of the sine wave. Oh, I guess I can't do that. The 2.5 times 10 to the minus 8 Teslas, that's the amplitude for the magnetic field oscillation. In what direction is the magnetic field pointing? The I hat direction. So of course it's oscillating. That really means the magnetic field is oscillating up and down along the x to negative x direction. And depending on where you are in the wave or what moment you pick to focus on, it might be up in the positive x or down, but it's along that axis. So how do we read all this? It's moving along the, oops, this is a mistake. There's a mistake here. Does anyone see what the mistake is? And I might want to look at another handout I have, see how I corrected the mistake. Yeah, that used to say y, and somehow it turned into an x. Right here, right in front of me, it's a y. So I'm going to change this. That was supposed to be y. I don't know how it got changed. Okay, let me back up. What was the mistake? How did I know this was a mistake once I started looking at it? And once I realized there was a mistake, I could find it. How can we tell this is wrong? As written, that magnetic field could never be the magnetic field of an electromagnetic wave. Because the magnetic field is oscillating along the I-hat direction, so it's oscillating along the x-axis, and yet because x is in the argument of the function, that means it's moving in the x direction. That the inside of the cosine is claiming that it's moving either in the positive or negative x, and the unit vector tacked on the end here is claiming that the magnetic field points in the positive and negative x, and those are supposed to be perpendicular to one another. So it can't be x inside and I-hat outside. That could never be the magnetic field of a wave. It could be some other arrangement, perhaps, which you do something different with charges and currents, but it could not be a solution to the sourceless Maxwell's equations. It would take current and charge nearby, probably current in particular, to do that, because that does not follow the properties of a magnetic wave, whereas this at least has a chance to, and that's what that was supposed to say. Okay, so what direction is the magnetic field pointing? It's along the x or I-hat direction. What direction is this wave moving? This is a wave moving in the negative y direction, because it's y plus something proportional to time. So as time goes up and up and up, we're adding more and more on to the y, and that means we're shifting the wave further and further in the negative y direction. As time goes on, this is a wave by graph transformation rules that's being shifted a greater and greater distance in the negative y direction. So this wave is moving maybe in like the negative j hat. If you wanted to ask, like, what's the velocity vector for the wave? The velocity vector would be negative c j hat. And this is the magnetic field vector. So what's the wavelength? What's the frequency? Basically, the coefficient of y, the coefficient of the spatial variable, or variables, the coefficient of the spatial part of this function is 2 pi over the wavelength. Y has units of meters. The inside of a cosine has to be dimensionless. So the coefficient of y would have to have units of inverse meters, and it's actually kind of like almost got units of like radians per meter, 2 pi radians per meter. So, from there, I would say, did I do that or did I not? My blank sheets. So from there, I'd say the coefficient of that guy is 2 pi over wavelength. What's the coefficient of time? Well, the corresponding concept to wavelength is, what's the wavelength? It's the distance to go through one full cycle of the wave. So what would the corresponding concept be for like time? It'd be analogous to wavelength would be period. What's the time, capital T, to go through one full oscillation of the wave? So this coefficient here should be 2 pi over wavelength, and this coefficient here would be 2 pi over period, which is the same as 2 pi times frequency. And either way, we could use either of those to get the wavelength, and from the wavelength to frequency, or vice versa. We could first get the frequency and from that get the wavelength. And how should these two coefficients be related? Here's maybe another way to write this. I'm going to get these numbers written down. And what is this kind of trying to just remind ourselves of? Magnetic field, a field is a function of position, but now we should be really clear. A field is a function of position and time. So it could be a function of all three spatial variables in time. Now, when I look at the actual function, it doesn't actually depend on x. It doesn't actually depend on z, which kind of tells me that it's not moving in the x or the z directions. It might be moving along the plus or minus y, and it's moving in the negative y. 2.50 times 10 to the minus 8 tests. I'm just copying this down before I lose it here. 1.26 times 10 to the positive 7 inverse meters times y plus 3.78 times 10 to the 15 1 over seconds times t, and that's all in the positive I hat direction. Okay. Go there a little bit closer. Okay. It's so hard to get this thing to not do that. Stop. And this thing's getting worse and worse. Okay. There's a couple ways you could write this. You could write this as B equals B naught, which I'm going to write as a vector. So B naught would be this with that. And I don't really care about a cosine versus a sine. I'm just going to write cosine. Either one would be perfectly acceptable solutions. So you could write this one of two ways. You could write 2 pi over wavelength times, a spatial variable, an x, a y, or a z. I'll say y minus, and if it's not minus, then it'll be flipped in direction, but I'll write it as if it's minus. Oops, almost right. This is moving in the positive y direction. And if we have a minus sign in there, if we don't have a minus sign, we have a plus, it'll flip it. And then this would have to be, must be a vector perpendicular to the y direction, the y-axis. So one way you could write it is 2 pi over lambda spatial coordinate, 2 pi over capital T time coordinate. You could also do it this way. What if you took my formula and you factored out 2 pi over lambda from the inside? So let's just bring the 2 pi over lambda out front and kind of like this. You see what I'm saying? Kind of like that. Sorry, it wasn't showing there. So this would just be y, right? But then what would the other guy be? Well, I got the 2 pi and I took out a lambda. So then this is lambda over t, lambda wavelength over capital T period times time. So lowercase t is the variable, capital T is a constant. So what's lambda over capital T? Well, 1 over capital T is the same as, what's lambda over capital T? Wavelength over period. What does that mean about the wave? This is how far it goes in this much time. How far does one peak travel in one period? One peak travels one wavelength in one period. So what is this? This is the distance that over time for like one cycle of the wave. This is, among other ways, this is lambda times frequency, right? Because the inverse, the reciprocal of period is frequency. So this is velocity. And of course, if it's an electromagnetic wave, we know that the velocity is c. So another way to write this would be, you don't really have to tell me lambda and t, right? Because they're related by speed of light. If you just told me one of them, the other one had better be a factor of c differing from it. Oh, cosine. So you could kind of always look at it like this. Like if you kind of factor out any other stuff, you'll always end up with like y plus ct or y minus ct, or some spatial variable plus or minus ct. And this is telling us that this would be moving in the positive y direction at speed c. So this is actually, the red one is moving in the negative y direction. And hopefully what should the ratio of these two guys be? If you did this one over this one, that should be speed of light. That should be 3 times 10 to the 8. That's a 15 right there. 10 to the 15 divided by 10 to the 7 would be 10 to the 8. And the 3.78 over 1.26 should be 3 for 3 times 10 to the 8, I mean. So they have the right ratio to represent not just something moving in a positive negative y, but moving in the negative y at speed, 3.00 times 10 to the 8. So we can do all that. So what do we get in this case? Let's see, I'll go back and actually get my wavelength. I would probably look at that and say that coefficient is related to the wavelength, but it's not the wavelength. It's got inverse units of length. It's related to 1 over the wavelength. So the wavelength is, for this guy, is 2 pi over 1.26 times 10 to the 7 kind of inverse meters, or you could say radians per meter. You could say 2 pi radians, and the radians would kind of cancel out dimensionally. If you like that, you could do that. And that is very close to 5, but like 4.99 times 10 to the minus 7, and the units come out to be meters. So that's the wavelength, and then I'll just kind of do the frequency here. I could do all sorts of things. I'll just do C over wavelength. So 3 times 10 to the 8th meters per second over the wavelength just found above. And 3 10 to the 8th over answer, enter. I got 6.02 times 10 to the 14 hertz, which is cycles per second. So that's a couple of those answers, and the wave's moving in the negative y. What part of the electromagnetic spectrum is this wave? The little header information said it was a laser beam. Let me just read it here. A laser beam is got a certain size and is turned on for 2 seconds then off. What part of the electromagnetic spectrum are we in here? Is this radio, microwave, infrared, visible, I'm missing one, ultraviolet, X-ray, gamma ray? This is 499 nanometers. Nano is 10 to the minus 9, and this is 10 to the minus 7. So this is 2 steps up from nanometers. This is hundreds of nanometers. So what kind of wave is this? This is in the visible portion of the spectrum between 400 and 700 nanometers. This is probably kind of greenish, maybe kind of bluish green, something like that. So this is a visible light laser. And then moving on to the next question. What was the next question? What's the frequency? What's the direction? What's the wavelength? Okay. The next one's, what direction does the electric field point, and write out the corresponding function for the electric field. So if this is the red equation for magnetic field, what's the corresponding equation? I'll just put it in green for electric field. And it is got to be proportional to the magnetic field. They point in different directions. They're scaled by a factor of c, but they're proportional to one another. So all this kind of complicated dependence on space and time has to be exactly the same. Otherwise, they wouldn't be proportional at all places and times along the wave. So that's not going to change. It's just the coefficient and the unit vector, basically just the amplitude vector has got to change. And then the rule there is to go from magnetic field amplitude to electric field amplitude, what do you do? To go from magnetic field to electric field, you multiply by c. To go from electric field to magnetic field, you divide by c. So I take this 2.5 times 10 to the minus 8 and I multiply by speed of light, 3 times 10 to the 8th. Well, the 10 to the minus 8 and the 10 to the 8 cancel out. 2.5 times 3 is about 7.5. So this is going to have an amplitude of about 7.5. And, you know, you could write volts per meter, you could write newtons per coulomb for electric field. So you're going to see a wave that's oscillating between positive 7.50, negative 7.50, positive 7.50. And what direction is that wave going to be oriented? Let's put a vector direction on this. So the rules here are E naught, I'm going to put that like without a vector. The magnitude, the amplitude of one is C times the amplitude of the other. In fact, that's not just true for the amplitudes, that's true at every point along the wave. Not just at the high points, but if B is halfway up to its peak, C is halfway up to its peak. If is zero, or sorry, if B is zero, E is zero right there. And then, you know, you could say there's a couple of different ways. E hat cross B hat is the velocity direction. So what way is this? This is definitely going to be something like K. And is it going to be positive K or negative K? This is the negative J hat direction. And this is the positive I hat direction. So which one would work out here for electric field? K cross I is positive J, but I want negative J. So I think we decide that this is negative K. Does that sound right to anybody? So this is, you can put the negative somewhere, but you know, this is amp, magnitude, and direction, or something like that. Another way you can say these two facts together is you can say this. I'll just write this kind of for once. This times this is this for magnitudes, but these are also perpendicular vectors. Velocity with magnitude C is perpendicular to magnetic field with magnitude B naught. So you could put these together and kind of as one fact, if you wanted to write it this way, you could write the electric field is the velocity vector cross the magnetic field. And in this case, the velocity vector is negative C J hat. And then you could just do your cross product and basically this has got like kind of B naught cosine, B naught I hat. That's supposed to be an I hat. So if you do that, I think you should again get that the direction is negative J hat cross I hat. JI is, did I do that right? Or maybe I don't have that right. Just a second. Nope, that's wrong. Does that look consistent with what we came up with before? Or does that look opposite to what we came up with before? Negative J hat cross I hat would have been positive K hat because I wrote this wrong. I wrote the vector cross product backwards, B cross V. That will get the directions right. It's kind of like you keep these kind of like you keep them in IJK, IJK, IJK order. So if one of the orders is EBV, you can kind of cycle that around, but B should always be followed by V and B should always come after E. So this is, I think, probably correct. Anyway, so you could write this as a vector statement, but that's just often for me broken down to be saying I multiply the magnitude of B by C and I make sure my right hand rules work and they're all perpendicular to one another. So this is the electric field oscillation that goes along with this magnetic field oscillation. And if you were to visualize it, you'd draw some kind of picture like you maybe have seen some of these in the book. Try to draw one down here. Try to draw one down here where it's black. So I'm going to draw this, and this is going to be the Y direction. Remember, the wave's not going to move in the Y, but it's going to move along the Y. And then I kind of want to get this right. Let's say I did X is towards me. X is towards me, and then I think if you do things well, Z would point upward. Does that look like a right-handed coordinate system to anybody else? I think it does to me. So I want to have the magnetic field oscillate along the positive X. So I'm going to kind of draw the magnetic field in the horizontal plane of this sketch as best I can. And at time 0, it'd be like at its peak. And then it would kind of go like this into the board like that, and out of the board like that, and into the board like that. Oh boy, it got terrible there at the end. So that's supposed to kind of look like it's in this plane a little bit. And that would be maybe labeled B. And now I'd like to kind of build up carefully. What should the electric field be? Well, the easiest spots for me to graph what the electric field should be is whenever one of them is 0, the other one's 0. Right? Because they're always proportional sizes. And basically, I now have to decide, let's say I hadn't already decided up here, I now have to decide if I want the wave to move that way, should I have electric field be up along the Z from here to here, or should I have it be down along the Z? And I can just try out those two right-hand rules. I'm just going to try, what if I had it be up in this little window of space kind of in here? So do I want it to be up while the magnetic field is out? And that would give me a positive Y. So I think I should have it go kind of down. When this is at me, this should be down, and it'll be kind of like this, kind of like that. And what this is supposed to represent to us is when the electric field looks like this. So imagine this is like a vector whose tail, all the tails of the vectors are on the axis, the y-axis, and then they're spiking out to hit the green curve or hit the red curve. So at one particular moment in time right here, this is what they look like. And I'm trying to make a little perpendicular symbol. And if you do green cross red right there, you get that your thumb is this way. And then you follow it, and for a while they get bigger, but maybe they stay pointing in the general directions they were pointing. And then for a while they get shorter up to like right there and into like right there. And then they're both 0. And then they both switch directions. And if they both switch directions, their cross product will stay in the direction it previously pointed. So this whole thing describes a wave moving this way with a velocity. And then, right, I'll just draw a couple more. So let's say I go to this moment, this Y coordinate, and now X is downward, or sorry, the electric field is downward, and the magnetic field is from the axis to here is kind of this way. And they're still perpendicular, and E cross B should again point leftward. E cross B is leftward. I'm gonna go to the main camera here. So let's see, what was I doing? I don't know, well, you guys can see this. Here's a fatter green. Is there a red marker maybe here? There's a blue. No. So I'll just do it across here. So I want the wave to go that way. So it's kind of like it's going like this, and then they switch, and it's going like this, and then they switch, and it's going like this. I did it kind of wrong. I had it and I lost it. They're flying this way, and then you kind of rotate 180 degrees, and they're flying this way, and you rotate 180 degrees, but they're all kind of going the same way. And at any point along the wave, we should be able to do the right-hand rule and come to the same conclusion about the direction it's traveling. Not, if it's true at one point, it should be consistently true kind of at all those points, at any point. And we would often call this a plane wave, P-L-A-N-E wave, because it seems like the value of the electric field doesn't depend on X or Z. So if you move a little bit this way, if you move from here to here to here to here, it's the same wave, electric field and magnetic field at all those locations. And you get a big like kind of wall of light kind of streaming this way. Okay, so what about energy and momentum, which is the bottom three kind of questions for FGH? What about these guys? What is the goal is really these two questions. G and H are really the goal. What's the energy in the pulse, and what's the momentum in the pulse? And notice that until you get to G and H, I think most of the questions were of the wave. What's the blah, blah, blah of the wave, of the wave, of the wave? But to answer G and H, you're going to have to tell me some information like this, like not just what kind of not just like how bright the light is, but like how big of a space does this laser cover? And this information here that's highlighted hasn't maybe gotten used in A, B, C, D, E, and it won't actually get used in part F either, but that information is going to be relevant if you want to know how much energy are you going to have to supply to the laser to create this beam, or vice versa. If you absorb this beam, let's say this light falls in a little solar cell, how much energy will be deposited in the absorbing material to gobble it up, which of course is the same amount of energy that it took the person emitting it with the laser to emit it. So how much energy does it carry? And that's going to have to do with not just the magnetic electric field issues, which we've heavily focused on, but also like some measure of the extent of the wave. So I would basically say, if you tell me this information about magnetic field here, I can tell you how bright the light is, like how bright the light is, like how bright the light is that hits the wall. But if you don't tell me how big the wall is or how fat the beam is, I can't tell you the total amount of energy that's hitting the wall. I can just say, this is kind of the brightness. And so what is the connection between electric field, magnetic field, which we can go back and forth with pretty well now, and energy issues? And the main answer to that question is you calculate this quantity called the capital S vector. And if you're keeping track of energy and momentum in electromagnetic scenarios, for example, an electromagnetic wave, you want to keep track of the S vector. And the S vector is named after a guy, Poynting. It ends up being a pretty good name, but it's a total coincidence. It's just a person's name, Poynting. But it kind of does point. So for some reason called the Poynting vector, for some reason capital S, and this is the definition of it. At every point, you take the electric field at that location and time, the magnetic field at that location and time, you do this calculation, and you throw in a constant. And somebody's asking, like, does light have mass? We'll talk about that in a little bit. We'll talk about things like that. I am going to say very clearly, light carries energy and momentum. And I think most people are very aware of the fact that light carries energy. That doesn't seem like too strange of a claim, I don't think. Like, you stand in the sun, you kind of feel like, oh, the sun's nice and warm today. Or you know that you got to have some power source hooked up to the lights bulbs to turn the lights on in the room. So light does have energy. Light also has momentum. Numerically, the amount of momentum is pretty small. So it often kind of is not very relevant amount of momentum for considerations of momentum conservation, but it's there. So we'll talk a little bit about things like, does light have mass? So what is this vector going to do? First of all, this does not have to be an electromagnetic wave. Any scenario that's got an electric field and magnetic field, you could go ahead and just do this formula and calculate this. What if you had a purely electric arrangement? What would the Poynting vector be? You had some charges sitting around, but they're not moving. They're static charges. There could be a very complicated electric field. But what's the magnetic field? There is no magnetic field. So what's the Poynting vector? If it's a purely electric arrangement, the Poynting vector is 0. If it's a purely magnetic arrangement, the Poynting vector is 0. If they're both around, it could still be 0, because if they both point in the same direction, their cross product could be 0. But in general, if they're both around, you get something. The Poynting vector describes the flow of energy and momentum in an electromagnetic arrangement. In particular, what direction is E cross B if we're talking about a light wave? That's the direction of velocity. That's the direction of travel of the wave. So the Poynting vector for an electromagnetic wave has funky units, but it's parallel to the direction that the wave is traveling. And what this is basically saying is, in particular for an electromagnetic wave, the vector S is parallel to the wave's direction of travel, or the velocity vector. And that kind of indicates that the wave is carrying energy along it forward. Because this is basically the direction that the energy is traveling, and it turns out to be parallel to V. So this energy and momentum must be accounted for when you do something to the wave. If you change the wave's direction, if you absorb the wave or emit the wave, especially absorbing or emitting the wave. And this would be related to things like, is energy really conserved in the process of emitting the light? Is energy really conserved as you reflect the light or absorb the light? And is momentum conserved? And these things are of pretty high level importance to physicists. Make sure that like we can account for all the energy and we can account for all the momentum. Momentum is related to force. So like this is basically saying to make sure we can account for all the energy issues and force issues, you might have to remember that there's energy in the light that you just gobbled up or that you just emitted. Okay, so how much energy and momentum? If you look at the dimensions of this, you'll come to the conclusion that this does not have directly units of joules, say. This is more like how bright the light is. So this has units of something more like joules per cubic meter or something like that. So not how much total energy in light, but how much energy is packed into every little pocket of light. But it actually doesn't have quite those units. This is basically the answer. The average value of the Poynting vector, because remember, if E is oscillating high, low, high, low, high, low, and B is oscillating high, low, S isn't a number. S is oscillating as you move along the wave. S is a big number at the peaks and troughs, and it's 0 at the 0 points. So it's going between 0 and a big number forward, down to 0, down to a big number forward, but it's always pointing forward because E cross B never changes direction in the wave. But it's oscillating between 0 and a maximum. And when you average it out, guess what the average value of S is if it oscillates between 0 and a maximum? It does so pretty symmetrically. It goes from 0 to the halfway point, symmetric to the way it goes from the halfway point to the peak. That's kind of what sine waves do. So the average value of S introduces a factor of a half into this. And that's basically reminding ourselves, don't just use the amplitudes of E and B because the wave isn't 7.5 newtons per coulomb everywhere. That's the biggest it ever is. And if you average that out, this averaging basically throws in a factor of 1/2 for sinusoidal waves. The average value of the Poynting vector is energy per area per time. And you can just kind of do the dimensional analysis on that formula and see that that is true. What is energy over time? Power. So what's energy over area over time? Power over area. So power over area is often called intensity. So it doesn't have its own unit, but like watts per meter squared or joules per second per meter squared. That's what S is telling you. So if we do S for the one we have, let me see here. For the one we have, the maximum value of S would be 1 over mu naught times the maximum value, oh, that doesn't have units, that doesn't have a power of 10, I mean, of the electric field times the maximum value of the magnetic field, which is 2.50 times 10 to the minus 8 Tesla. I'm not going to worry too much about the units. Put in the 4 pi times 10 to the minus 7, and the units will come out to be what we're saying they are. So if I put in the value of mu naught and all that, I got 0.149. And the units here, what I'm most used to is thinking of this as watts per square meter, or you could say 0.149 joules per meter squared per second. And by the way, when I did this multiplication, I just multiplied the amplitudes of these vectors. I didn't actually do the cross product, but that's okay because this is a cross product of two perpendicular vectors. So the magnitude of the cross product is then equal to the magnitudes multiplied. And so what is S really doing? S is going from 0 to S max, back to 0, back to S max, back to 0, back to S max. And the average value is going to be, the intensity is going to be half of the maximum value, or it's going to be the average value, so half of that. 0.0746 about joules per meter squared per second. And I would encourage you to think of this is like how bright the light is. Like if somebody shines this in your eyes, it doesn't matter to you that the beam of light is like way wider than you and you're casting a shadow on the wall behind you. All that really matters is how bright it is. I mean, that's what you're going to react to. This is kind of like the brightness intensity. But what if, so that's intensity, and that is part F. So basically, what is the intensity? The intensity is the average value of S, and in a wave, in an EM wave, this will definitely be 1 over mu naught times electric field amplitude times magnetic field amplitude, but the averaging gives you a half. And then if you wanted to, you could of course say, well, E naught is C times B naught, or the other way around. So you could kind of swap out all sorts of variations. You know, remember E naught is C times B naught. So there's all sorts of kind of variations in there that you can do. And then you get a lot of C's and mu naughts. And you might also want to remember that how are C and mu naught related? You might just kind of want to remember that at any point you might use the fact that C squared is 1 over epsilon naught times mu naught. So given this swapping, you can kind of pick whichever two you want. Do you want some version with a C and a mu? Great. You don't want C? Okay. So you could write this like all sorts of different ways that are all saying the same thing. It's basically proportional to the amplitude squared, because it's amplitude of E times amplitude of B, and they're proportional to one another. It's basically proportional to amplitude squared. There's a factor of 1/2, and then there's constants to keep track of. But which constants you go for might have to do with, are you trying to answer intensity, or are you trying to answer a question related to intensity, like total energy? So I would probably myself find the I value, basically the S average value first, and then I would just sit there and think, okay, now what question was actually asked? And maybe the question that was actually asked was total energy carried in the pulse, total momentum carried in the pulse. Don't I have one of those? Kind of cover this up a little bit to get that there. Okay, so how do we get from intensity to energy, total energy? This is where we're going to need this stuff up here about how big the wave is. So what do we have to do with intensity to get an energy? We have to multiply it by an area and a time. So what area and what time should we multiply it by if you kind of just read this stuff here? At every point across the front of the laser surface, it's this bright. But how big is the extent of the front? It's a circle of radius 4 millimeters. And for how long is this intense light going to fall on the wall? Or for how long is this intensive light going to hit the viewing screen? It's going to hit it for 2 seconds. So basically, I'd say in this case, maybe we should probably say in this case, this is not electric field, this is now energy, and you're just supposed to know from context, total energy, that would be the total power times the time, the power times the time, and the power is the intensity times the area, the cross-sectional area. So in this case, it's the intensity times a circle, which is 0.004 meters in radius, right? That's my area, and I turned it on for 2 seconds. So I should take the intensity and multiply by this kind of pickup factor. Pi times 0.004 for radius squared. That's an area, a cross-sectional area. The area of the beam is around 10 to the minus 5 square meters. And then I multiply that by 2 seconds. And basically it's the area, the I value times 1. This happens to be very close to 1.0, almost 1.01 times 10 to the minus 4 meters squared seconds. And then you could just multiply that out, but I'm just going to list all sorts of stuff. What's the power of the wave? What's the energy of the wave? We'll just list all sorts of things. Intensity we had was 0.0746 watts per square meter. If I multiply by that by the area, the cross-sectional area, I got 3.75 times 10 to the minus 6 watts. To go from here to here, I multiplied by area. And then to go from here to here, I'm going to multiply by time interval. And it's basically just kind of following your nose and looking at the units and make sure you're kind of multiplying by the appropriate area or length or time or something like that. And this comes out to be very, very close to 7.50 times 10 to the minus 6 joules. It's a fairly bright light, but it's only on for like 2 seconds, like on off 2 seconds. So this is a lot of energy summary information related to energy issues. The easiest one to get your whole hands on is I, because that's kind of what the S vector pretty much directly represents, or the average value of S is I. Watts per square meter, watts, which is joules per second, and then joules. One other summary we might do is, another way to think of how bright the light is energy density. So like if you kind of pictured this big, see how this is kind of like a big tube of light heading this way? How long is the tube? Well, what's the area here? That's A equals pi r squared. How long is this beam of light? And by long, I mean like in space, how long is this beam of light? How far has the front edge of the light moved in the time that you turned it on and then turned it off? It's been moving at the speed of light, and it was given 2 seconds. So this whole thing would be like C times delta T. Like that would be kind of like the length. It would be kind of like C times delta T. So you turn it on and off for 2 seconds, and you'll end up with like you could almost like picture it as like a solid tube of light stretching out, spiking its way across the solar system with this shape. It's a cylinder of light, and the whole thing's moving at speed c. And I drew it left because it was the negative y direction. So what's the volume of all this? The volume, or I'm going to write it as delta V, is going to be A times delta L, which is A delta T C. So what is the energy density? That would mean energy per unit volume. So to go from here to here, we're going to divide by volume. But if you look at what we just did, to go from intensity to power, we multiplied by area. To go from power to energy, we multiplied by delta T. And to divide by volume, we're going to divide off the A and divide off the delta T. So you could divide by all that stuff, but really start to finish, how are intensity and energy density related? I don't care the extent of the beam. To go from here to here, you divide by C. That's overall what's going to happen if you kind of do all those steps. So you could do it step by step and then find the volume and divide by the volume, or you could say it should end up being 0.0746 divided by the speed of light. And then if you think about what that would do to the units, what units do you get if you take watts per meter squared and then you divide by meters per second? Watts per meter squared, and then you divide by meters per second. Well, that's the same as multiplying by seconds per meter. And a watt is a joule per second. So this is a joule per second times a second over meters, meters, meters. So this comes out to be joules per cubic meter. So how intense the light is very much related to how much energy is packed into every little square millimeter of the light. And this is 2.49, I think I'm seeing this right, times 10 to the minus 10 joules per cubic meter. And the bigger you want to make the beam this way, cross-sectionally, the more energy it's going to take. And the longer you want to have the beam on for, the more energy it's going to take, because you're making it a larger volume of light. And every bit of the volume of light is like kind of like this, juiced up with energy. So that's kind of like 4 different quantities, all with different units, but related to one another, that could be used to talk about how much energy is in the light. Of this list of four, let me see. Of this list of four quantities, which ones are, if you've ever heard this terminology, intensive measurements and which ones are extensive measurements? Which of these four depends on the extent in space and time and the space of the beam, and which ones don't? The two purple ones, you don't need to know the size of the beam to answer the two purple ones, but you need to know things like what's the diameter or what's the time of the beam to answer the non-purple ones. Okay, that is the energy side of things. And I've been saying it's energy and momentum, energy and momentum. So what does it mean to say that light carries energy? It means that when it hits your skin, you kind of warm up a little bit. You know, that might be one takeaway thought. It means that, you know, if you put some cool device down in the path of the light, you could maybe convert this amount of energy into, from light energy, you could put it into some other form of energy. Maybe you could put some little solar cell in the path of light and have some mechanism and some thing going on, photovoltaic thing, that converts that much energy into electrical energy. And then maybe you can use that electrical energy to lift a heavy box and turn it into like potential energy of gravity. So there's energy in the light. And if you're going to emit the wave, if you want a higher electric field wave, you're going to have to pump more energy into your emitter system, whatever your emitter system is. Basically, you're going to have to move more charge around, or the same amount of charge at a faster speed, and that's going to cost you kind of like more. Somehow you're going to get more kinetic energy into the moving charges, which then is handed off to this rippling thing called the electromagnetic wave that heads outward from the charge moving system. You know, when you get right down to it, almost every process on Earth is powered, if you kind of think of it ultimately, because there's this big thing called the sun that's just dumping gobs of energy into the Earth system all the time. Name a type of power plant. Think of it like, let's see, where does the energy come from to run the air purifier that I can hear humming away in the side of the room? Where does the energy come to do that? I'm just picking some use of energy nearby, and that's the one that caught my attention. Where does the energy come from to do that? Well, I see that it's plugged into the outlet, right? I see there's something over here plugged into the outlet right down there. Like, oh, it's grabbing its energy from some electrical reservoir of energy that's available to the room, just like the lights are and the projector and the computer and whatever else. Where does the energy, how does the energy get in the power grid? You know what I mean? Somewhere on the other end of the power lines, there's a power plant. And now we could imagine a couple different types of power plants. At this point, the discussion, I think, will go differently depending on which type of power plant we picture on the other end of the power lines. So what kind of power plant do you want to picture, just for the purposes of discussion? Somebody's saying hydroelectric. So what does hydroelectric power plant mean? Hydroelectric. So they're creating energy, they're in the form of electrical energy at the other end of the power line somewhere. And let's say it's a hydroelectric power plant. So they're probably using induction to take the motion of water, maybe falling over a waterfall or falling downhill. They take the motion in the water and they use that to spin something, and via induction, they hand the energy off to electrical energy. So basically you could say, like, what form was the energy in before the power plant got a hold of it? I would either probably say kinetic energy for moving water, or maybe potential energy because the water was up high on a hillside and then it was moving because it was up high heading downward. So it was like mechanical energy, kinetic or gravitational potential energy in the water. Why is the water up high? We get a lot of energy by spinning things, flow of energy. Yes. Why is the water up high on the hillside? Because if it wasn't up high on the hillside, you can't really run your hydroelectric power plant. Why isn't all the water long ago in the history of the Earth just worked its way downhill? Because it works its way downhill and then it gets like a lake or something, or it gets to a puddle, or it gets to an ocean or a sea. something like that, at a lower elevation than it used to be. But it doesn't just stay there. The sun heats the environment up, and you evaporate the water, and it floats upward, becomes a cloud, and then the cloud rains and it's high on the water and just keeps the system going. So we, at some point, almost no matter what you pick for your mechanism of use of energy that you see around you, if you just kind of like rewind that back in time and just ask yourself, okay, right now, the energy is in my Clif Bar. What form was the energy in before it got into the Clif Bar? And before that, what form was the energy in? Almost always, you're going to find yourself landing on the sun at some point. Like, you're going to work your way back to, well, you know what? The plant had energy in the plant because the plants had little chlorophyll in the leaves, and it goes through this process called photosynthesis, where it, via a natural mechanism, not a solar cell with electrical wires connected to it, via this natural chemical mechanism, it converts energy from radiant light energy from the sun into chemical energy stored in the plant. And maybe you eat the plant and then you got the energy, and then you run somewhere. Or maybe you don't eat the plant. Maybe a cow eats the plant and then you eat the cow, and eventually you get back to the sun most of the time. Unless you were to say a nuclear power plant, I'll say that. Anyways, just to kind of say, like, where's all this energy coming from? It's coming from the sun. Ultimately, the typical value given for the intensity of sunlight is around 1,300 watts per square meter. And we could use that to figure out questions like typical value for intensity of sunlight is much, much higher than this. So this is not very intense light. I mean, sunlight's not super, super bright. It's not like, and of course, don't look right at the sun. It's bright enough to cause some damage, but it's around 1,000 watts per square meter. And we could use that to then say, okay, so how much energy is the Earth absorbing every second? And to go from, so energy per unit second, so how much power is the Earth absorbing? Well, let's just assume it absorbs all the energy. It doesn't bounce any of the energy back into space, which actually bounces a decent amount of it just kind of back into space. If you absorbed it all, we would want to take the intensity of the sunlight and multiply it by some area. What area should we multiply the intensity of sunlight by to come up with the energy that Earth is absorbing? Something like the cross-sectional area of the Earth. If you're standing on the sun looking at the Earth, it's taking up a certain amount of area from your perspective. So it'd be like pi r squared for the Earth. Not 4 pi r squared, by the way, the surface area of the Earth, just like how much cross-sectional area this marble called the Earth presents to the streaming sunlight. And it doesn't present 4 pi r squared of surface area to the streaming sunlight. It presents a cross-section of pi r squared. So you can do that. You can find that's how much power the Earth is absorbing every second, or has falling on it every second from the sunlight. You can go from there. Okay, let's talk briefly about momentum, though. What does it mean to say that there's momentum in the sunlight? There's energy in the sunlight. It hits the Earth, and there's all this energy being made available to Earth processes all the time. And you stand in the sun, you feel yourself get a little warm or something like that. That's an example of maybe energy considerations. What about momentum considerations? What is that claiming? I'm claiming that the laser pulse, the sunlight, the light coming off of the stuff up here, it's not only carrying energy around the room or around wherever, it's also carrying momentum. How do you notice if you absorb momentum? How does something behave if it gobbles up some momentum? Its motion changes. So let me ask you this. Have you ever thought of this question? Maybe the sun's kind of up in that part of the sky, I'll say just for purposes. Like, oh, I can feel, that feels nice. The energy in the sun kind of feels nice. Have you ever thought something like that? I would think maybe you have. Have you ever thought, oh my gosh, the sun's kind of in the southern half of the sky and I need to walk south, so I got to push against the sunlight to kind of make progress that direction. Have you ever thought that really? Like the light bulb is kind of pushing me away from it? Because that's what we're claiming is also happening. Is that the light as it travels outward has some momentum, and when it hits you, you absorb the momentum and you kind of recoil backwards a little bit. And that's true, but the amounts are very, very much smaller. And typically, it wouldn't be too surprising in this kind of scenario to find out that something is smaller than something else by a factor of something related to the speed of light. So this is intensity, power, total energy, energy per unit volume. For each of these guys, there's a corresponding way to talk about momentum considerations. And what would the name for these momentum considerations be? Energy, momentum. Energy and momentum are direct kind of partners in this game. So I'm going to kind of, just like this one's written 1, 2, 3, 4th, I'm going to write 1, 2, 3, 4. Number 3 is going to be total momentum, just like number 3 above is total energy. How do you get from these to these? To go from here to here, you divide by the speed of light. And you can just check that that works dimensionally. What do you get if you take energy units and you divide by velocity units? You get momentum units. So I'm just going to tell you the momentum is take each of these numbers here, divide each of them by the speed of light, and you'll have a number down here. So the total momentum is this total energy divided by C. And the total energy was already 10 to the minus 6 joules. And now I'm going to divide it by 10 to the 8th per C. And it's not going to be very big. So the total momentum has units of, or has a value of 2.50 times 10 to the minus 14. How do you write momentum units? There's lots of ways. I'm going to write Newton seconds. That's one way to do momentum units, among others. And to go from all of this stuff to all of this stuff, you divide by C. And when you divide by C, the numbers get a lot smaller, and we're much more aware of this in the light waves than we are in this in light waves, but both have to be there, just like the electric, just like you have to have the electric field and the magnetic field. You can't have the E's without the energies without the momentums. What are the other ones? Well, this is energy density, and you divide by C. Probably this one would be like momentum density. So I'm not going to write the number in there, but that would be momentum units over volume, cubic meters. Okay, let's just name these other two. And I think the easier way to do this is, what do you get if you take power and divide by speed? What units do you get for power divided by speed? You actually get a force. I'm just going to tell you, you get a force. So this is the force that the light is applying to the things that it hits. Or this is the force you have to apply to the light to kick it outward from the laser in the first place. And this should have units of newtons. And that should kind of work because we said to go from power to energy, you multiply by delta T. And to go from newtons to momentum, you're going to multiply by time interval. You're going to go from newtons to newton seconds. So from here to here, you're multiplying by delta T. From here to here, you're multiplying by area, if you look up above. So what do you call force per unit area? Because that'll fill in number 1. What's force per unit area? This is kind of like an overview of all sorts of, quantities of things. So this is going to have units of newtons per square meter. That's called a Pascal. And force per unit area is a pressure. So what we're saying is the sunlight, the light hitting hitting the screen, the projector screen, is dumping energy into the screen, and the screen's probably heating up a little bit, but it's also applying a pressure to the screen that's kind of pushing it this way, pushing it back. But if you put the number in there, you're going to find it to be an incredibly small amount. It'll be this number divided by C. I'm going to write that one in 0.0746 divided by the speed of light. And the pressure is measured in pascals. It's 2.49 times 10 to the minus 10 pascals. Atmospheric pressure is 101,000 pascals. So this is really hard to notice, but it's there. And then just one last thing to say. what is intensity divided by C? Pressure, right? But here we also did the same thing. We said, just staying up in this top grouping, we said intensity divided by C is energy density. 2.49 times 10 to the minus 10 joules per cubic meter. 2.49 times 10 to the minus 10 newtons per square meter. And if you look at that, that's the same thing. So in a light wave, pressure and energy density, those have the same units, by the way. This is something you'll probably talk about in like fluid mechanics, fluid dynamics, like pressure and energy density have the same units, and in a light wave, they're the same amount. And you could talk about all these things. These tend to be very, very small, and unless you're in a certain regime, this tends to be really unimportant, and probably all you really care about is this, but you can't really do one without the other, is what Maxwell says. So I think I'll kind of leave it there. So from this, we could answer questions like, how much energy is the board absorbing over some interval of time, or a solar cell, or something like that. And it's all basically proportional to electric field amplitude times magnetic field amplitude, which is basically the amplitude squared. But which factor you throw in depends on, did you square the electric field or did you square the magnetic field, and what quantity do you want to calculate? This one or something like that. So I think we answered each of those and a couple more. All right. No class on Wednesday, advising day. And just an encouragement to stick with all the social distancing stuff. That's probably getting a little, we've been doing it for a couple months. Maybe it starts to get easy to forget for a minute or two, but it will help our campus, keep us meeting in person as long as possible. So I know a couple people that are quarantined at the moment, either just getting back or just starting.
Thank you.
Yeah, thanks, Reagan.